Welcome back to Engineering Mechanics, for which we are now starting a new part, and we call this part the race because everything that we have done before was effectively a warm-up, since it is content you should have been familiar with before. We did the warm-up, however, because it's always good to have a common baseline. But now it's time to tackle the race and to really look at structural systems like engineers do. So far, we mostly dealt with physics, and physics, of course, is the base for what we're going to do here in the race too. But we now have to talk about how engineers define structural systems and how they deal with them. Therefore, the pace of the class will pick up a little bit. Don't get me wrong, we of course continue to consecutively explain the terms to you, and we also give you consecutive problem statements that you can grow with the problems here in this class. But the name for this part here is not something that I came up with to begin with. It's something that the students gave me as a feedback, because they were telling me that I should signalize to the students that this is really where the effort in the class lies, and that this is significantly more in depth than the material that they have seen before. Of course, everything is easy once you know it, but that is exactly why we call it the race that we now need to go into, because we will not see content that you have dealt with before, most likely, and we need to learn some new concepts. Of course, the mathematics will stay very simple. We try to use very simple numbers, but it is my experience in the classroom that sometimes students struggle with the definition of the concepts and so on. But if you consecutively pay attention and you already picked up to this point here, then it should be a walk in the park for you, as long as we don't let anything slide. So based on student feedback from previous classes, this is my, I don't want to call it a warning because there's nothing that I need to warn you about in this class, but here's my word of caution that this is the part of the class that really requires some new thinking and some new approaches to these concepts that we will show you. And this is particularly important because we will move forward with assuming that everything we learned in the previous lecture is available for the following lecture. So I put a lot of effort into really consecutively building this up rather than just throwing topics at you. So there is a structure here, but therefore it's much more important that you really stay on top of your game and you stay with the content of the class. So what I'm trying to tell you is, don't move on to the next lecture if you still have a question mark somewhere about the previous lecture. So this is really designed to get you through the race and to make sure that you are able to reach your goals of this class. So with that said, I think we're ready to tackle the race now, and let's get ready to have some fun and start our brand new topics of what I would call true engineering mechanics. All right, I think it's fair to say that this is where the fun really starts in engineering mechanics, because today we will talk about rigid bodies in equilibrium. And of course, you know a lot already about equilibrium, but the reason this is exciting for me as your teacher is because one of the first things we need to talk about and we need to calculate is called support reactions. And those support reactions are often not really explained from the ground up. So, for example, while I had a fantastic mechanics teacher back in my days, I was not really systematically taught how to interpret these support reactions and how I connect the physical world to the world on my piece of paper. So I had to kind of pick that up on the way. And yet I was asked to really make sense out of all the problems that were given to me. So today it is therefore my goal to really introduce support reactions to you and really do that from the ground up. I find that very important because it makes no sense to calculate something if you have no physical interpretation of that. At least in the engineering world, it doesn't make sense. And you will learn that we need to use rotational equilibrium, which you're already familiar with, to actually calculate these support reactions. And it is my goal to really explain to you why the rotational equilibrium applies to these kind of physical systems. Ultimately, of course, our goal for the next 3 lectures and also for your upcoming homework is to really determine the support reactions. And we want to understand today how we deal with concentrated loads. I will define that, of course, for you, what that is. And then in future lectures, we will talk about things like distributed forces and other types of load cases. But for now, let's just talk about a general introduction to support reactions. And because I'm not able to meet you in the classroom with my props, I now went around town and took some pictures for you. For example, here of a railroad bridge. So in part A, you see the railroad bridge, and then you can see the red box and the blue box, which zoom in on the actual support reactions, which I magnified for you here. And although it's kind of hidden here, this picture still shows a slight difference between the left support and the right support. And the reason I actually picked this picture, although you cannot fully see this support, is because we can beautifully see this type of support. And I first want to talk about this kind here. You can see that on the concrete, which builds the foundation, if you will, for this type of bridge, there's a steel plate. And then on top of that steel plate, you have something that can actually rotate or move, because there is effectively a hinge here, and we'll talk more about hinges later, but you see there's a bolt here, so this entire contraption on the bottom can actually move about this point, and this part is also not connected to the bottom steel plate here. Now, sadly, we cannot see this behind the brick wall here. It's kind of hidden, but you will see in other pictures that this part here is actually not allowed to sit freely on this and is actually bolted down. And when that is the case, we call that a simply supported bridge, and I will explain to you later on what simply supported means. But for now, please understand that here on this part, you actually have a friction plane, whereas here you are completely bolted down to the ground. Let's take a look at the next picture. So here we see actually a parking garage, and a parking garage now consists kind of like a Lego system of many parts that are stuck together. And for example, here you can see that there is a pedestal, which is magnified right here, and there sits a concrete beam on top of it. And notice, please, and this is why I highlighted this, notice this little black portion here. That's actually a neoprene pad, which allows the concrete to sit and move in certain ways. And next time you go into a parking garage, pay attention. You can actually see this over and over again. And just for example, I pulled out another picture here, and it's not that easy to see, but the trained eye can find these neoprene pads, and they also guarantee that these elements are actually simply supported. And that will become more clear as we move through the lecture and we see some other pictures. But for now, let's just understand that we as engineers need to develop a solid interpretation of these different support systems, and we need to be able to put them on paper so that we can calculate our numbers based on the real physical world and the real interpretation of these systems. And let's move on to the next page and look at some more pictures about that. So here we have another set of images that can help us to study and learn more about support reactions. Let's zoom in and take a look one by one. So here first you can see a stadium or multi-story building, if you will, in which we have staircases that connect the one floor to the one above, and therefore they need to be supported. These staircases were pre-built and pre-made, and they were just delivered to the construction site and then pretty much put in place. And because they were put in place, they need to be supported by these pedestals once again. You have one on each side. And what you cannot easily see in these images is that there's also a neoprene pad or something else underneath here, because engineers would never allow that the concrete just sits on top of the concrete. There has to be a friction barrier or something that actually allows friction to easily be overcome or motion to overcome. And we talk more about this when we talk about the degrees of freedom. So engineers want to make sure that if, for example, this part of the structure is exposed to heat and it extends or changes its shape or its dimension, that it still does not affect this part of the structure negatively. So this portion has to be somewhat decoupled from this portion, and the way engineers deal with that is with, for example, neoprene pads that then create a certain support reaction or a certain type of support reaction. All right, let's move on to our next image here, or set of images, for which we can see a ongoing construction site. And the reason I picked this picture is because you can see a beam here on the top. This is similar to the bridge, conceptually speaking at least, that we saw initially. But in this case, we have a very specific type of connection here, and that is magnified right here in the blue. You may be able to see that it's actually welded together. So there's definitely nothing allowed to move between this portion of the structure and this portion of the structure. And this can be executed in other ways as well. So for example, here on the top, if I zoom into that part, you can see a connection. This one was executed through bolts, but it's the same concept. This part of the structure and this part of the structure are rigidly connected to each other, and we actually call that fixed. So that is a very important word to understand. So here we talk about a fixed support or a fixed connection, depends on how you look at it. And here's just another one which sits down here. And I think through this image, you get the picture and you get the concept. Let's take a look at one other famous structure here on campus. And this one here actually also has a connection up here, but in this case we can only guess because it's behind the building cladding. However, you can see a beam here that is supported, and you can actually see something that is supported here as well. And it also helps to support the roof from here to here. So it's an entire structural system, but that structural system definitely has a connection and a support reaction up here for this roof. And my best guess here, I cannot see inside, but my best guess is that it's also a fixed connection, but we really would have to go and dig into it to really see what's going on. However, you have now seen actually all three types of supports that we will deal with in the future. And the ones that I'm talking about here for this class are called rollers, pins, and fixed supports. So these are the three types of supports that we will deal with in this class, and you kind of have seen them already. Of course, I didn't tell you that because our goal here today is to actually idealize them. But in a general sense, this support here could be probably represented by a roller or a pin. In reality, it's a roller, but sometimes engineers use it as a pin. This one here would also be a roller or a pin. This one here would, without a question, be a fixed support, and so would be this one. Actually, all of them that are highlighted here are fixed supports, and that makes the structure very rigid, which is why I believe that this one here must be also a fixed support because of this overhang that you have here, and that needs to be supported at these two columns. But you have now seen these rollers, pins, and fixed supports as they are be seen in the real world and where they are located. So before we really define what these are and how do we differentiate them, we can look at a general concept and think about how the forces actually do apply at these support reactions. So for example, if you think of this beam here, how does the force come to these supports and how much force do they have to carry? And we will do that with an introductory example on the next page. All right, so what we usually do in the classroom is we run a little experiment at this point, and I want to show that to you here on the left side. So I will draw a bathroom scale that I usually bring into the classroom, and I asked one student to step on it. And that student, of course, shouldn't be afraid of giving away his or her weight. And the last time we did this in the classroom, I had a student that actually measured 170 pounds. So 170 pounds were measured by the scale. Then I bring a second scale, and I ask the student to verify that the weight is really properly measured with the 170 pounds, and I ask the student to also step on that one so that we can use both scales equally. And what we find there is that the student still has a weight of 170 pounds. While my bathroom scales are not always super accurate, they are accurate enough in this situation to actually measure the same numbers here. So why do I need them to be accurate? Because next I will ask the student actually to step on the two scales in a different way. So let me copy these bathroom scales here. One I put here, and then the next one I put right next to it. And what I do then, I ask the student actually to step on each scale with 1 foot. And I ask a second student to come in and report to us the real numbers. So 1 foot is here and 1 foot is there. And now think about what happens. We usually have a slight disagreement about this in the classroom, but usually we agree to it afterwards. And I want you to think about where the disagreement could be. So what do you think these bathroom scales would read right now? Exactly. Each one of them would read the same number, and they both would read 85 pounds. So the left one would read 85 pounds and the right one would read the very same. And this has something to do with force equilibrium. Sometimes students think because if you stand on a scale, you have to actually spread your legs, right? So you have your left foot on this scale and the right foot on this one. So therefore you think that there's a force component that kind of pushes more, or at least that's what some students think. But at the end, if this is F student, then of course here you have F student over 2, and here you have F student over 2 as well. And so we can usually agree on that for this concept. But then comes the next part where I kind of repeat the experiment, but in this case I move the scales a little bit further apart. So let's move one scale right here, and then the second one I move, let's say, 1 foot apart from one another. So I usually bring in my tape measure and measure that the distance here is really 1 foot. And then of course again I ask the student to use one scale under each foot. So that looks like this. So now we have the student standing on there, and then I ask the other student again to read what the scales tell us. And yes, you guessed it, for the very same reason that is true here, even if you spread the legs further, of course, you have to read the same number. So we have 75 pounds here, and we have 75 pounds here. And that should make sense in a general context. So last but not least, I asked the student this one more time to actually put one scale right here and then the second scale very far apart. In fact, I usually bring in my tape measure and make sure that they are actually 60-inch apart from each other. And then the student looks at me funny and says, hey, I'm not on the cheerleader team, I cannot do that. So we need to break off the experiment. But I say, no, don't worry. We can actually make this work, because I then usually bring in a rigid body, and the rigid body comes in the form of a wooden beam that I put on the scales. So let's draw the wooden beam on here. That looks something like this from the top. And I use some spreader beams underneath it to make sure that the load is properly introduced into the scale so that we can get accurate readings. Another thing that I do actually is I make sure that I now zero the scales. So now I actually make this a 0 reading, so 0, and I also make this a 0 reading before the student actually steps on it. And then I ask the student to step at the center mark, so put 1 foot here and 1 foot there. And then I asked the rest of the class what happens now to the readings of the scales. And I let them think a little bit about it, and then we move to this table here. So let's go ahead and put the student actually on the simply supported beam that you see here that idealizes my structure. So I have a force here with 170 pounds last time we did it in the classroom. And then I have a distance of 30 inch here and a 30-inch distance here. Please take a look real quick. The simply supported beam or the rigid body I actually idealized with the solid and the dashed line here. I will talk more about this later on throughout the lecture, but from now on, just understand that it's not a cable, it's a rigid body. And a rigid body always has what we call a reference fiber here, the dashed line underneath. So you always need to include that. And what you will calculate later on is what is always called here in this case RAY. So R for reaction, A as point A, and then Y in the Y direction. Therefore, here on the right side, I call this RBY. R for reaction, B at location B, and Y in the Y direction. So these are obviously the scale readings. So this is equal to the scale. And this is the left scale and then the right scale. So let's take a look at the numbers that I last time collected actually in the classroom. So I will now present to you the numbers that we measured in the classroom. And there is some imprecision here, so don't get confused about that. That's just because my equipment as a bathroom scale is not real engineering equipment, but it gets the point across. So we measured 90 pounds on the left scale and we measured 80 pounds on the right scale. And you can see on the very far right, we totaled it for each of our measurements. And in this case, we ended up with 170 pounds. Now, that is not a surprise because it's a symmetric system and students would have guessed that. But then I asked the student to actually step on the 20-inch mark, which let's pretend is right here. So now the student with 170 pounds steps there. We have 20-inch right here. And that leaves us with 40-inch right here. And then I asked the student to guess what happens before the second student actually gives us the scale readings. So go ahead and think about what you would answer in the classroom if I would ask you in this scenario what the left scale and the right scale would read. All right, now that you thought about that, my next question in the classroom would be, hey, which one of the two support reactions, RAY or RBY, would be larger? And I want you to pay close attention to this because when I ask you this, it's very clear to you, but sometimes in exams, it's not that clear. But if you really think about it, you probably would say that this needs to be larger than it was before, and this one needs to be smaller compared to this scenario. Why? Because the 170 pounds moved closer to this support and further away from this one. And in fact, when we recorded it in the classroom, we actually found that the left support now measured 112 pounds, whereas the right side measured 58 pounds. And while this is not super precise numbers, they still totaled up to 170, which was a good thing for us to find. All right, next I asked the student then to move to 40-inch mark. So let's put the student on the 40-inch mark, which let's pretend is right here. So there would be the 170 pounds right there. That leaves this with 40-inch and then this with 20-inch. And we obtained measurements for that as well. Of course, you already understand that now this support on the right side needs to become larger. In fact, it needs to be larger than even it was up here. Whereas the one on the left side needs to be lower. And if you pay closely attention, you already see that it's effectively the same system as this one, just flipped around. So you should kind of see the same numbers again. But when we measured it in the classroom, we ended up with slightly different numbers, which was 57 and 113. But again, a total of 170. Then the student is asked to step on the 50-inch mark. So let's put the student right there with the 170 pounds. 170, which leaves us with 10-inch here and 50-inch here. And now, if you already think in your head, hey, I clearly understand this concept, which hopefully you do, spend 3 seconds, 5 seconds before you continue the video and ask yourself if you could predict what numbers we measured here in the classroom. So go ahead and do that. And here we go. All right. So you probably agree with me that this force now needs to be larger than this one. So the right scale needs to be even more than 113, but certainly it needs to be less than 170, right? So you could at least approximate it. But if you already understand the concept, then you could even calculate it precisely. I'm not doing that yet. I will do that in a little bit. But you would find that the right scale in the classroom actually read 142 pounds. And then we had 31 pounds on the left side. And you will find that this sums up to 173, which again is due to the imprecision of our equipment, but the physics is still true. So technically there's some error in here and some error in here. It should be 170 as well. So let's just pretend that this here is roughly 170. Last but not least, I asked the student then to step on the 60-inch mark. So that the student would be standing here, and then we had 60-inch right here. And yes, you absolutely guessed it. There is a 0 here and then a 170 here for a total of 170. And two very important things to take away from this table. Number one, what comes up has to come down at some point. So this is effectively equilibrium in the vertical direction. So you can say the sum of the forces in the vertical must be equal to 0. That is the first thing we take away from this. And then the second thing we take away from this is the closer the force moves to the support, right? The closer it moves to a particular support, the larger the number will become until it hits the maximum here in this case. And likewise, the further away the force is from the support, the less force you will find in this type of support. In fact, you might see a relationship between the geometry of these problems and the scale that, in fact, you might see a relationship between the geometry of these arrangements and the scale readings that were returned to us in the classroom. And if you do not see that, please try to think about this for a second. So I'm going to move on in a second, but please pause the video and try to find a relationship between the geometry and these numbers. That is something that I will explain further down the road. But for now, let's just remember that from this table, the two things we can learn is everything that goes up has to come down. And the closer you come, the more force you support. All right, so with that said, we can now move on and take a very specific example out of the table. And the one that I want to pick is where the force was actually sitting at the 40-inch mark. So I draw my seemingly free body here, and I had a support reaction RAY here. I had another support reaction here RBY, and I picked the case where my force was sitting at 40-inch with 170 pounds, so that the geometry looks as follows. I had 40-inch right here and 20-inch right there. And now the question is, why are the numbers as they are? And you may already have guessed it, or you may already have seen that in the table. There is a relationship between the geometry and the numbers that the scale gave us, but the question is why, right? So if you want to try something, it doesn't hurt to write down the sum of the forces in the y direction being equal to 0, and usually upwards positive, right? So therefore 0 would be equal to plus RAY plus RBY. And by the way, I always start my equations with my unknowns, and here I have two unknowns, and then minus 170 pounds. So notice that I have one equation with two unknowns, so I cannot solve this. I mean, it's a good thing to write down because it definitely helps you to understand the physics of the problem, but I obviously cannot solve this because I have two unknowns in the same equation. So the question then is, what can I do next to find RAY and RBY? And Then, of course, the students say, hey, we have a second equation usually, but the second equation would be sum of the forces in the x direction is equal to 0. And in this case, we have nothing that acts in the 0 direction or in the x direction. So therefore, x does not even exist. So what do we do now? Like, why does physics still work? And the answer is we have one more equilibrium or one more concept that we have not explored yet. And that is actually moment equilibrium, right? So moment equilibrium. So far, the only thing we have done with moments is we calculated moments, like we called it acting moments. But now we want to use the moment to actually find the answer for our support reactions. So I asked the students in the classroom to apply moment equilibrium to the system without any further guidance. And so what we usually end up with then is an equation that says, hey, why don't we just take the sum of the moments about, let's call this here point C, about point C. And of course, we'll take counterclockwise positive, and we say that's equal to 0. And then the equation will read what? 0 is equal to RAY multiplied by 40 inch. And we also have RBY, which has a lever arm of 20 inch about that point. But now we need a directional sense. So RAY turns clockwise, which makes it negative if we turn about this point. And RBY, which turns also about this point, would rotate counterclockwise, and that makes it positive. So let me assign those signs here. And now I can actually state, hey, I have equation 1 up here, and I have equation 2 right here. And I could now solve two equations with two unknowns. So this can be solved, and this is a valid way of dealing with these type of problems. But there's obviously a smarter way or a easier way, and engineers like to work less, I guess. So therefore, we need to find a way to reduce our calculation effort. Don't get me wrong, mathematically, this is obviously super easy, but maybe we can make our life even easier. And so what do we notice in this equation number 2? We notice that 170 was not part of the equation because we would have a lever arm of 0, right? And so why can I not change the location to turn one of these into 0? So for example, if I take the sum of the moments about point B, then this one would disappear. If I take the sum of the moments about point A, then A would disappear, or RA would disappear. And so if I want to calculate RAY, what I really would be doing as an engineer, I would take the sum of the moments about point B being equal to 0, counterclockwise positive, and then I can say 0 is equal to, let's say, RAY, I always start with my unknown, still turns clockwise, so negative, and has a lever arm of 60. So minus RAY multiplied by 60 inch. And then I have my 170 pounds multiplied by 20 inch. And this one turns actually, let's see, it turns counterclockwise, so therefore it is positive. All right, and now I can solve this equation, right? So RBY is not even part of it. So I now solve the equation for RAY, which is equal to 170 pounds divided by 60 multiplied by 20. These are 2 inches. Both of them are inches, I should say. And so we actually have 170 pounds times 1/3. And if I calculate that out, it would come out to be 56.66 pounds. And that is very close to what we found in the table up here, right? So we actually found that we have 56 in this case, or I guess we actually should flip this around. We actually looked at this case here, so 57. So 57 is very close to what we found here. And the reason why the scales measured this is not just force equilibrium, but it's also moment equilibrium. And let me talk a little bit more about moment equilibrium and why we need support reactions. So the reason we need support reactions is we need to prevent this entire system, this rigid body here, which you can think of as a bridge, we need to prevent it from falling down, we need to prevent it from moving left and right, but we also need it to prevent rotation. So this rigid body cannot rotate. So just like the force equilibrium prevents a system from falling down or going up, rotational equilibrium prevents a system from rotating clockwise or counterclockwise. So we could use this equation here to state that this is in static equilibrium. It does not rotate. Therefore, the sum of the moments is equal to 0, and therefore we were able to solve it using this equation. And that's why we actually found what the table suggested, or what the scales suggested in the classroom. We found the very same answer with the very same relationship. For completeness reasons, let's go ahead and actually also calculate RBY using this method, just so that you can see how it applies and so that you can verify your results. So let's go ahead and find the equation for RBY, which we would do by the sum of the moments about A in this case is equal to 0, and that is also counterclockwise positive, and then 0 would be equal to RBY multiplied by 60 inch, and this in this case would rotate counterclockwise, so therefore it's positive. And now the 170 rotates clockwise, so I multiply that by negative 170 pounds and by 20. No, that's not true. It's not 20. It's actually 40 inch in this case, right? It must be the inverse. So therefore, I can now calculate my numbers. So my RBY is equal to 170 pounds times 40 divided by 60, which then comes out to be 113.33 pounds. So that, once again, is what we found in our result table, and it's not a surprise that I can now go back to my initial equation here, the sum of the forces in the y direction, and if I plug in RAY with 56 and RBY with 113, then this will be equal to 0. So I might as well check that one off. So check. So that is actually what engineers do in the real world when they, let's say, have to calculate the bridge based on like a truck that's driving over or something like that. They use the moment equilibrium for finding one of the support reactions. Then they use the second moment equilibrium equation to find the other ones. And then they use this formula here, the sum of the forces in the y direction, to check, right? So obviously it's tempting to use this formula and then plug the value back in here, which is acceptable. But I would recommend that you use these two approaches to then check your value here at the end. But we'll talk more about that when we solve actual examples. What we need to understand here is that we used the sum of the moments about point B, so about this point, to make RBY disappear from our moment equation as we had it set up here before. That was one thing we need to understand. And then the other thing is we need to understand that the rotational sense, right? So the rotational sense that we define here really defines the science here. Sometimes students are very tempted to define a negative and a positive based on the direction. So for example, here RBY goes up, therefore it's positive. RAY goes up, therefore it's positive. No, this goes out of the window now. It's only dependent on the rotational sense. And that's why RAY here is actually negative and it rotates clockwise. Therefore, it's negative, right? Remember the right-hand rule. That's where it's coming from. And probably more obvious this will become when you look at the 170 here. Because here, because you rotate about B, it's positive, right? So you have this force times this lever arm. So it's a positive rotation. Whereas here, in this equation down here, RBY, it actually becomes a negative rotation because it turns clockwise about this point. And so please do not fall into the trap of following the direction of the arrow. Some people would say, hey, 170 points downwards, therefore it's negative. And that's what you see here, but that is not the full story, right? The negative does not come from the fact that the 170 is pointing downwards. The negative only comes from the fact that the 170 rotates clockwise about point A. And that is an important concept to understand. But I think we now understand where these numbers come from and how equilibrium works, in a sense that we can use rotation as well for equilibrium condition. And that is what engineers use to really calculate the support reactions of, let's say, a bridge. And with that said, we now have a general understanding of where support reactions are. We now understand how we can calculate them. So the last thing I want to do for you is to define the differences between the different support reactions. So later on, you will not see the pictures anymore like this here with the arrow up and the arrow up here. We actually have symbols that represent specific support reactions, and I will now define those for you. So as promised in the introduction, you get some better pictures of the actual supports. Earlier, it was just my goal to give you a general overview of the structure and the location of the supports. Now I want to talk about the differences between the supports. As mentioned before, here you can see that this part is actually sitting on top of the steel plate, and this is actually allowed to rock. And it's actually called a rocker sometimes, or a roller. So let's call this here a roller support. So roller. So this is a roller support, sometimes also called a rocker. And I think the picture speaks for itself, right? Why it's called a rocker. Now I want you to pay close attention, because there is actually an axis in here about which the system is free to rotate. So you can have like rotation in this direction. And also, since we're talking about this right now, which later on we call degrees of freedom, you may understand that this system is not restricted to move in this direction. So there's a degree of freedom in that direction. The only thing that the roller prevents from happening is actually a vertical, in this case, direction. So there would be a force that is resisted in this direction. So the only thing that this support resists is the vertical direction. Now let's take a look at the picture to the right of it. That one also has a very similar look, and yes, there's also an axis of rotation about which the system is free to rotate. But now please take a look at the plate here on the bottom. There's no sliding like here. There's actually a bolted connection. And what that means is that we need to use our red color here, I guess. So I have restriction in this direction. It is definitely not able to move in that direction, but it's also not able to move in the vertical direction. So these are both restricted degrees of freedom, if you will, whereas the purple one here is still allowed to happen. Now, that one we call a pin, because the only thing that is free to rotate is the rotation, right? Or the only thing that's allowed to move is the rotation. So it rotates about that pin. So think of this axis as the pin. So you would say, hey, this one here has a pin too. Yes, that's true, but it also is allowed to roll along this axis. And now you guessed it, the last one here is called a fixed support, because in this case, all our aspects are prevented, right? So for example, this direction cannot move, it's restricted. Then also it cannot move up and down. And in this case also, because of these bolts here, which connect this beam to, let's call this here the support, right? So the column here is really the support in this case. So we have the beam that is rigidly connected to the column, and therefore we actually end up with a system that cannot rotate and cannot turn about a pin axis. So those are the three different systems, and now I prepared some more pictures for you just so that you get a better variety of it. And let's take a look at them and appreciate the differences. So I love this picture here, because here we have a rocker or a roller, whereas here we have a pin, not very clearly to be seen. but you can see a difference between this one and this one. And so here I really talk about a roller. So roller. And then here we have a pin, and then here we have fixed. So let's talk about those more. So here you can see it's actually a 3D arrangement. This here is an arc of a bridge. And there's a abutment here where the pin is clearly to be seen here. This cannot move parallel to the surface. It cannot move vertically to the surface. It can only rotate about this axis, and therefore it's a pin. This picture you have seen before. This is a fixed support because this connects these two elements rigidly. And then we talked about this here earlier. This is really the neoprene pad, which really is a roller. Sometimes it's used like a pin, but you can probably understand that if this part here, this part of the beam only sits on this neoprene pad, it's really free to move left and right. It can rotate down, it can rotate up. It's just supposed to allow motion in the horizontal direction in this case. And then here's a beautiful picture of a pin, which is a 3D pin, where you can see this plate here is actually attached to the ground. And then this part here is coming from the structure, and they are pinned together here. And you can see the entire structure right here in the background as it looks like. So there's pinned. And then last but not least, we have another corner, which is fixed support. So let's complete this, and let's say that this is a roller. And then here we have a pin. And then here we have fixed. And that's our supports. And I believe those provide a beautiful overview of the general support types, which now you have a clear physical interpretation of. And you can now differentiate between the roller, the pin, and the fixed support. But on the next page, I want to clarify how these images are idealized by engineers on a piece of paper. So now, last but not least, before we solve problems, we need to understand how these support reaction types are idealized on paper. And we already talked about all these terms. So let's take them one by one and define them properly. So here for the first row, what you see is a variation or a different variation of a roller or rocker. And so this roller, as you can see, is symbolized by two parallel lines. And really what those two parallel lines symbolize is the friction plane, or the plane in which the system is free to move. So if I apply a, let's say, coordinate system to the entire roller, then let's say that for this one here, I have a x-axis, and then here I have a y-axis. But really the way engineers think about this is as parallel and perpendicular components. So therefore, let's draw it for this system here as well. So we have, of course, an x-axis, which happens to be parallel, and a y-axis that happens to be perpendicular. And notice that I am usually nice enough to also draw these circles on top of it. In some textbooks, you find them represented as such, but this symbolizes to me that it's actually free to rotate about that point. So notice that we can move in the x direction, we cannot move in the y direction. And yes, this picture is not super clear. It prevents upwards motion and downwards motion. Some people think it could lift up because there's nothing that prevents that. But as you saw, for example, for the railroad bridge, it's heavy enough that there will be no uplift for sure. However, motion in the x direction, no motion in the y direction, and motion is possible in the rotation about the z-axis. And I represent that with these circles usually. Before I move on and fill out the rest, since we're talking about this, please note that here this looks very similar for, of course, what we call the pin later, right? So this would be the pin. But the difference between the two is the parallel sliding plane, right? So that's clearly visible if you compare this picture to, for example, this picture, or this picture to this picture. But let's first complete our row for the roller now. So we have degrees of freedom, and the degree of freedom in this case is really in the x direction, right? And that is probably the more obvious one to see because the picture nicely shows the plane. But keep in mind the circle here and the fact that this part of the beam is actually free to rotate about this point. So therefore I have a second degree of freedom for this one, which would be rotation about, and important, about z-axis. Because keep in mind that technically the z-axis comes out of the plane to you, right? And we therefore always call that counterclockwise positive. Now the restricted degree of freedom in this case leaves only one of them, which is the y direction. Or better said, actually perpendicular to sliding plane, right? So, and that completes the roller. Now for the pin, I don't think we need to talk much more about these pictures here, only the difference that we already addressed, the difference between the sliding plane and not having the sliding plane. So the way I think of them is like this here is like standing on a roller skate, whereas this one here is standing on golf shoes. So the golf shoes actually dig into the ground, whereas the roller skates can actually slide across the surface. And therefore you know that here now you have another restricted degree of freedom, which is not just the y direction, it's also the x direction. So let's actually add a coordinate system here so that we agree on that. So I usually would end up with an x-axis here and a y-axis here. And then I can write that I have restricted degrees of freedom, for example, in the x direction and in the y direction. And so what engineers are usually after is the parallel and perpendicular component to support surface, right? To surface. So that is what we want to know. However, just as the roller, the pin also has the circle here, and that means this thing is allowed to move and to rotate about the z-axis. So therefore we have a degree of freedom that is free. I know that sounds like double free degree of freedom, right? But it gets the point across. So we have rotation about z-axis. And last but not least, let's take a look at the symbol for our fixed support. So here we see the fixed support, and what's different now, we remove the triangle and the circle, because the circle, or for some people the triangle, indicates free rotation, but this now is really like fixed. So this is like you holding your pencil in one hand and not letting it rotate out of your hand. That is exactly what this shows, and of course this can be under an angle or vertical, it doesn't really matter. But that we call fixed usually. So let's complete the table for that. So this would be fixed. And degree of freedom, we have none here, as long as we're talking about 2D, of course. But we have x direction as restricted. We have the y direction restricted. And we have rotation about z-axis. And just to be very clear here, just because we don't have that on this page, just understand that we have a z-axis that comes out of the plane somewhere. So for example, here we would have z, but we do not consider that in 2D. So third dimension not considered in 2D. Therefore, we just use clockwise or counterclockwise. So clockwise or counterclockwise. And I think that explains this table and now gets us ready to really interpret these results and teaches us how to read the different support reaction types and how to idealize them on paper. So let me just finish with the restricted degree of freedom is usually what we try to find. That is what we usually are after as engineers. And so let's maybe write that here on the very side. So the restricted degree of freedom is what we try to solve for. So we engineers in this class, I should probably say, solve for the restricted degrees of freedom. Degree of freedom. So now we understand their physical interpretation. We saw many pictures of different support reactions. We understand how to idealize them. We understand how to read the symbols. So therefore, we are now ready to tackle problems in which we are asked to solve support reactions for rigid bodies in equilibrium. In fact, that is the thing we're going to focus on for the next 3 lectures. All we are asked are to report support reactions in different scenarios. And once we're done with that, we will actually move on to what's called internal forces. But to understand internal forces, we need a solid understanding of support reactions. And that is what we will from now on tackle in our example problems. So let's move on and start our first example problems for support reactions. All right, welcome to real engineering mechanics, as I would call it, or the problems that really make my heart sing and probably the heart of every structural engineer. What you see from now on are probably the topics that either make you fall in love with structural engineering or hate it. But of course, I'm a structural engineer, so I love it, and I think it's really fun to determine the equilibrium of these force systems. So here we are asked to calculate the support reaction for the steel beam that has 3 loads on it, 20 pounds, 30 pounds, and 40 pounds, and then has, of course, given distances for each of these forces. And the first thing we always have to do when we see these problems is to draw the free body diagram before we can actually solve it. And what I do to help myself with this is usually I kind of bring down the dimensions. So let's do that first. And here we go. My next force and the end of the beam. And then I have to draw my free body diagram. And remember what we talked about, that the free body diagram is now representing a rigid body, and a rigid body always has a dashed line to identify it. You will learn more about this later, but for now, just apply a dashed line on the bottom. Sometimes you can put it on the top later on, but for now, just put it on the bottom. All right, now we have to look at the symbols here, or the representation in the picture. This here could either be a pin, a rocker, or a fixed support, and this one here as well. But the symbol or the image gives away what it really is. This one here allows the beam to slide on top of it, so therefore it's clearly a roller or a rocker. Whereas this one here has the pin actually in there, and it prevents horizontal motion, vertical motion, so therefore this would be the pin. In other words, we actually have to represent the forces in our free body diagram now. So obviously I need a force that is acting in the vertical direction. I call that RAY. But because it's a pin, right, I also have to add a force in the horizontal direction, and I call that RAX. And then because we have a roller on the right side, I only have one support reaction, which then is RBY. And for my free body diagram to be complete, I need to add my forces. So I add those. And of course, I properly identify them. And now I'm done with my free body diagram. Now I can go ahead and solve this problem based on my free body diagram. And what I do is I want to find RAY, I want to find RBY, and I want to find RAX. And RAX would be calculated as the sum of the forces in the x direction being equal to 0, and 0 is equal to plus RAX, and therefore it's equal to 0. That is already an answer. But please note that I still calculate RAX to be equal to 0. It's a result. All right, let's find RAY. Remember from our explanation before that if I want to find RAY, I need to make RBY disappear. So I take the sum of the moments about this point. So I write down the sum of the moments about B is equal to 0, counterclockwise positive. And then I say 0 is equal to RAY multiplied by, I need to bring down my lengths here. So let's actually do that. So we have 3 feet here, 6 feet here, 2 feet, and 1 foot. And now I can use those dimensions to calculate my lever arms. So the entire structure is 12 feet long, if I'm not mistaken. Therefore, my RAY has a 12-foot lever arm. And now the question is, does RAY turn clockwise or counterclockwise about this point? It turns clockwise. Therefore, it's negative. And now I have to deal with all my other forces. So let's start with the 20. So 20 pounds multiplied by, what distance do I have here? So from here to here I have 6, 8, 9 feet. So times 9 feet. The question is that positive or negative? And the answer is positive because it turns counterclockwise. Then I have my 30 pounds multiplied by, what's that distance now? From 30 to B, right? So which is here, that would be 3 feet. So I multiply that by 3 feet. And that is also counterclockwise, therefore it's positive. Last but not least, I have 40 pounds, which is no secret at this point, is also positive. And that has a lever arm of 1 foot. And now I can solve the equation. I can just state that RAY is equal to 20 times 9 plus 30 times 3 plus 40 times 1, and the whole thing divided by the entire lever arm, 12. And please notice the physics of the entire equation, right? So I have pound times force, pound times force, pound times force, and that needs to be true for all of them. So it's a moment equation, which is indicated here. But now I take moments and divide them by 12 feet, right? So just to be clear here, what we have is we have something that is pound foot divided by foot, which then of course returns foot, which is good, returns pound, which is good because we obviously want to find a support reaction in pound. And if I calculate this out, I will find that my answer is really 25.83 pounds. And that qualifies as a result, so I double underline that and use my answer arrow. And I have my first result. Let's do the same thing for the other equation for RBY. So to calculate RBY, I take the sum of the moments about A to be 0, counterclockwise positive, and then 0 is equal to plus RBY multiplied by 12 feet. And now minus, let's start from the left again, minus 20 pounds multiplied by 3 feet minus 30 pounds. And just for those who are puzzled, let's just write it as 3 plus 6 feet. And last but not least, minus 40 pounds multiplied by 12 minus 1, if you will, or 3 plus 6 plus 2, which is really 11 feet, right? And so I can now rearrange that equation as well. And so I can find that RBY is equal to 20 times 3 plus 30 times 9 plus 40 times 11, and this whole thing as well divided by 12. And if I calculate that out, I will find that RBY is equal to 64.16 pounds. And that once again is a result that I have to not just double underline, but I also have to verify it. And I want to talk more about the verification in a second. So now I can use my force equilibrium to really verify this result and to actually be sure before I turn in my exam or my quiz that I'm correct, right? So I can say that the sum of the forces in the y direction is equal to 0, and 0 is equal to plus RAY plus RBY minus 20 minus 30 and minus 40. And what you will find is that this here is equal to 90 or negative 90, and that these here are equal to plus 90, and therefore I can check it off. And I am certain that I didn't tell you anything wrong here. I actually found my correct results. Let's talk about this for a second again. So please understand that you always have to report 3 results for these support reaction problems, right? So you always have to provide RAY, RBY, and RX in this case. Of course, this might be different. So for example, you can have the pin on the other side, you can have the roller somewhere else. So the letters might change or the arrangement might change. But for us in this class, for now, you always have to report 3 results. We will learn more about this in future lectures, but it is a given in this class that you always have 3 support reactions. Otherwise, the system would not work for reasons we do not understand yet, but believe me that the system would not work if you don't find 3 support reactions, even if the support reaction ends up to be 0. And so one thing we want from you here is that you can identify where the horizontal support reaction is. So for example, if you would have placed the horizontal support reaction here, which sometimes I find students do in an exam, that is of course not correct, because here you have the roller and not the pin, and therefore you would lose points. So please understand that, and also understand how the equilibrium moment equations work as they are exemplified here. And then last but not least, understand that we have a moment divided by a lever arm, and that turns it back into a force. And I believe that completes this example, and we are ready for our next one. So here we can see our next example problem for a simply supported beam with, in this case, 2 forces on it, and you are supposed to find the support reaction at A and B. Notice that this is already given in symbolization form. So here you have clearly the pin because there's no sliding surface, and here you have clearly the rocker or roller because the roller is having the sliding plane right here. So that means that the horizontal force would be resisted at A, whereas vertical forces are resisted at B and A. And notice that the force on here are not just vertical, they're also horizontal. So there is a force component that acts in the horizontal direction that must be resisted at A. And I think that allows us now to draw the free body diagram. So let's go ahead and do that. And of course, again, this is a free body diagram. Therefore, I need to use my dashed line because it is a rigid body. And I have support reactions RAY, in this case RAX. And by the way, it doesn't matter in which direction you assume RAX or RAY, because notice that here I'm just assuming. I mean, intuitively, all of us know that the force is going up here, but you don't know if RAX is going to the right or to the left unless you have some experience. But what I'm trying to tell you is it doesn't matter. You could even assume RBY to go downwards in this case. but that would just make you find a negative answer for RBY. All right, now I have forces acting on there, so I have 10 Newton in this direction, and I have actually my life easier if I break it down into a vertical and a horizontal component. So let's call this here 50 Newton times sine of 30. And then I also have a horizontal component which is equal to 50 cosine of 30. And now we can write out the equilibrium equations for this system. Let's go ahead and do that. So first, let's find RAY. It's the sum of the moments about B being equal to 0, counterclockwise positive. And therefore 0 is equal to minus RAY, negative, right? Minus RAY multiplied by the lever arm, which happens to be 4 plus 1 plus 2, so that's 7 meters. And then minus 10 Newton. And the lever arm now is 3 meters times 3 meters. And minus, be careful, because it's only the vertical component that creates a force. So I need to take this entire system here, right? So the 50 Newton. So in fact, I color code this just this last time. 50 Newton multiplied by sine 30. And then that needs to be multiplied by the lever arm, which relative to B is equal to 2 meters. All right. Okay, so now you could calculate that out. I don't even have to do that right now. So RAY is equal to something. Just conceptually, I'm going to show you how to find RBY, which is the sum of the moments about point A being equal to 0, counterclockwise positive, and 0 is equal to plus RBY times 7 meters. So that's the entire distance between RBY and the support A. But I actually already made a mistake here, so let me fix that. It's not positive in this case. It's actually negative because I assumed my force to go clockwise about this point, right? So I assumed it downwards, remember? It doesn't matter how you assume it, you just have to be truthful in your equation, and I wasn't here, so I need to actually make this negative because it turns clockwise. So negative, and if you wanted to put in parentheses to understand it's a rotation, then that is fine. And now I can use my other two forces. Let's start from the left. So minus 10 Newton multiplied by 4 meters, because I'm turning about A, and minus 50 Newton multiplied by sine 30 multiplied by 5 meters. And you can calculate what that comes out to be, RBY. And then, of course, don't forget to check these, right? So you would run a check. And the check would be the sum of the forces in the y direction being equal to 0. And 0 would be equal to plus RAY minus 10 Newton minus 50 Newton times sine 30. And then be careful, now it's minus RBX. But what you will find if you solve this is that RBY actually, so let me fix that. RBY here. So what you will find is that RBY is actually negative. So that force will be minus something, and of course in Newton. And this one here will come out to be positive something in Newton. But because you found that this is a negative answer, you have to plug in a negative here as well. And then negative and negative gives plus. Because in reality, this support reaction will push up. And you cannot change physics, right? In fact, that's something you need to always keep in mind when you solve these problems. You always need to think about the physics behind it. And it is so easy to check your results, for example, using this equation, and to make sure that your physics checks out. So please do that and understand that if you were, for example, to plug in a positive number here and then you subtract it, that this equation cannot be zero unless you made a mistake in your calculation. All right, so we have two results so far. Let me actually double underline them. We have this result and we have this result down here. But we need a third one. Remember, we always need three support reactions, and in fact we need RAX. And so to do that one, I do the sum of the forces in the x direction being equal to 0. And 0 is equal to my assumed RAX, so plus, and I sometimes use a double plus, so plus RAX. And let me explain that to you. So this one here says that my RAX is positive in the sketch sense, right? So I sketched it positive, but it's also positive in my directional sense, which I did not indicate here. So now I indicated it. So this positive comes from here, whereas this positive comes from the sketch. And that sometimes helps me to check myself. And now what acts against that is the minus 50 Newton times the cosine of 30, right? And so you can now solve this equation and find that RAX is really equal to positive in this case, because they are actually acting against each other. This pushes to the left, this pushes to the right. So I find a positive result for this one because they have to be in balance. And therefore I find that my answer here, without really calculating it myself, is plus 50 cosine 30. And that is a result as well. And therefore I now have my three results and my three answer arrows that I need to indicate that I solved the problem. And therefore we now completed our entire problem here, for which we were supposed to find the support reaction. I leave the numerical values up to you. Of course, you're more than capable of finding the right answers here and conceptually thinking through it. But this completes this example, and we are now ready to move on to more complicated examples. So here we have our next fun example, which usually causes confusion in the classroom simply for the fact that we now have a support reaction that sits in the middle under the beam. And please notice this half circle. It's not a full circle that would actually turn this into a hinge, and therefore this part of the system would be unstable if there was a hinge here. So there's only a support underneath it and not in the beam. So we have the pin here on the left side, we have the roller or slider on the right side, and we have an overhang here, which makes the problem interesting because now you have to be careful in which direction it rotates. But let's take a look at it and draw the free body diagram real quick. So the free body diagram would look as follows. Of course, my rigid body must have a dashed line. And I need to indicate that I have my roller on the right side in this case. So this here would be RBY, and it has no other support reaction. RAX right here and RAY right here. Now let's take care of the forces. So I have the 20 Newton acting right here. And then once again I have two force components. One is going down, and the other one I might as well draw here. It points to the right and it points down. So here we have 100 times sine 70. And here we have 100 times cosine of 70. And now I can use those to calculate my support reactions. Let's go ahead and do that. So I start in this case with the easiest one, which is RAX. So to find RAX, I use the sum of the forces in the x direction being equal to 0, positive to the right. And 0 is equal to plus positive RAX plus what's positive actually as well is 100 cosine 70. And so what you will find is that you actually now have to invert RAX. So you find a negative RAX. Or even better, you will find that RAX is equal to minus 100 cosine 70. And that comes out to be negative 34.2, in this case, Newton. And it's very important to understand what the negative means, right? The negative does not mean that my arrow is pointing in the negative x direction. It's very tempting to think that, especially in this case. But what this really means is that in this equation, I assumed my RAX to be incorrect. And remember where this plus comes from. This plus does not come from a positive x direction. It comes from the fact that I defined everything that goes to the right to be positive. And so now with that definition in mind, I find that my RAX is negative. And since it is negative, I actually have to flip it around. And yes, in this case, it coincides with a negative x direction, but this is not always the case. Please keep that very much in mind. So this is very important here, that I have a negative here. And what that really means for my drawing is that my RAX is pointing in this direction with minus, well, now it's positive, 34.2 Newton. That is my real answer here. And please also note that in sketches, you never use a negative number. So never put a negative 34.2 in the right direction. Always put a positive 34.2 in the left direction. All right, the same is true for all the other equilibrium equations. Let's go ahead and solve those. So let's, for example, find RAY, which is the sum of the moments about point B being equal to 0, counterclockwise positive, and then 0 is equal to, I always start with my unknown, which is negative because it turns clockwise in this case, minus RAY times 4 meters, that's 3 plus 1, right? Plus 20 Newton. And now about point B, so I'm taking the sum of the moments about this point, so 3 meters times 3 meters. And now I need to consider the 100 times sine 70. So 100 times sine 70. And that needs to be multiplied by 2 meters now. But let's pay close attention to the rotational sense. It rotates about this point and it's going down, and therefore it rotates clockwise, which makes this negative. So this needs to be a negative number. And let's spend some more time thinking about this, although I said it before, but I'm rotating about this point, right? So notice that this is a negative force and this is a negative force, or I should better say it points in the negative y direction. Both of them point in the negative y direction. But here my 20 has a positive sign and my 100 sine 70 has a negative sign. And so you can see here that this sign is not affected by the direction of the force, and by direction I mean the y direction. It's really dependent on the rotational sense. You can call that a rotational direction as well, but this one here turns about this point clockwise, negative, and this one turns counterclockwise, positive. So that's what you see here in this equation. And you can solve this equation now for RAY. So RAY in this case actually happens to be, believe it or not, negative 31.98 Newton. And what does the negative mean now? That means that I was wrong here as well, right? I assumed it to go up. That's what I assumed here. Up, notice that here the negative up stands for rotational direction, not for the up direction. But I find that it's negative. And the negative here tells me, Raphael, you were wrong about assuming that it's going up. You actually have to make it go down. And therefore, I have to say that 31.98 Newton in the downwards direction. And that is my true result here, right? Because I never use negative numbers in sketches as an engineer. That is a no-go. So I have that answered. And actually I have this one answered too here. So let's put that with description. And last but not least, I need to find RBY. I could use force equilibrium, but I choose to use the sum of the moments about point A being equal to 0, counterclockwise positive, and then 0 is equal to RBY, I always start with my unknown, turns counterclockwise, therefore positive, has a lever arm of 4 meters. Now I need to consider the 20, so the 20 Newton, and that is multiplied by 1 meter if we turn about point A. Yes, and then we have a rotational sense that is clockwise, therefore it's negative. And last but not least, I need the 100 sine 70, which has a lever arm of 1 plus 3 plus 2. So 1 plus 3 plus 2 meters, just to have that properly in your notes. And that is turning clockwise, therefore it's also negative. And if you solve this now, you will find that RBY turns out to be positive 145.9 Newton. And that is a result that tells me that I was right about my assumption. So the positive tells me, Raphael, you assumed correctly, and I know that my support reaction 145.9 Newton is actually going upwards. And that is my ultimate result here, which I now have to provide with an answer arrow. And that completes all 3 of my answers. Of course, if I were in an exam right now, I would certainly run a check. So my check here is the sum of the forces in the y direction being equal to 0, and 0 is equal to, careful now, because the first one is going down, right? So minus 31.98 plus, no, that's not true, minus 20 plus 145.9 and minus 100 sine 70. And that comes out to be minus 0.04 something, but that is equivalent to 0 in an engineering sense, and that works out. So we now solve this problem as well, and I think you have seen another variation of these support reaction problems where you may have to flip your direction of your original assumed sense. In fact, that was true here as well, so let me highlight that here as well. So we have here 31.98 going down. And that is important that you understand that and properly indicate this, so you always include this arrow and show me which direction the force is actually acting. But this completes this problem, and I think we have one more left for today, and then you're ready to solve your homework. So here the fun gets a little bit more intense, but I would say also a little bit more fun. So what we have here is a structure with different 90-degree angles that has 2 forces acting on it. And what makes this problem so interesting is that we have the supports at a different elevation. So this here is higher than support A, for example. And therefore, this support reaction has a lever arm about this support as well. And these problems come in really many different variations, and you're really encouraged to set up your own problems and try them, because I can even show you this one right now and you can understand it completely. But my experience in the classroom is as soon as we change something a little bit, so for example, we bring the support reaction a little bit further down, so maybe down to here, then the student might be a little bit more confused or again confused. So it's really important that you grasp the concept and study these problems. Now, I'm not going to solve this problem entirely for you. I'm just going to give you some hints here, and I want to talk about the actual support reaction. Of course, you understand that here on the left you have the roller, which means you have RAY acting in this direction, and then on the right side you have RBY, and you also have RBX in this case. You can also call them vertical or horizontal, it doesn't matter. RBY and RBX. And now, in the previous problems, you always had a choice, or you could solve one before the other or the other before the one. In this case, you really have no choice about this, and you understand that if you solve the problem, you have to start with one of these two. And I'm not going to tell you which one right now, but you will find that if you solve, for example, for the sum of the moments about this point, you have two unknowns that enter the equation. You have RBY and RBX that rotate about this point. If you rotate about this point, you only have one unknown here. Both of them can be solved depending on how you set up your equations and how you set up a system of equations, but there's an easy way and a hard way to solve this problem. And again, understand that the reason RBX has a influence on the moment about A is because you have an elevation difference between A and B, right? And that makes this problem really interesting. I will now give you the answers to these problems. So for example, RBX comes out to be, and I do this in random order, by the way, this is not how you should solve them. So 30 Newton would be the answer here. And then we have RAY, which comes out to be 26.54 Newton. And last but not least, we have RBY, which comes out to be 146.7 Newton. And I really encourage you to solve this problem and to pay close attention to how you go through it. This has many learning opportunities built into it. This is the reason why I'm not solving it for you right now. I want you to really go through those aha moments yourself and see how the knowledge applies without me showing it to you. So please go ahead, have some fun with it. And once you've done that, I'm sure you're ready to tackle your homework and to solve any support reaction problem that is for simply supported systems. I will now move on to talk about the upcoming homework, and I wish you good luck with this. Let's finish off the lecture by the very importance of the takeaways and the questions that are still muggy to us. And there's no other lecture where this is more important than this one, because everything we're going to do from here on will rely on the concepts that we applied today or that we introduced today. And therefore, rather than moving forward, if there's something still muggy to you, I highly suggest that you move backwards and make sure that you understand whatever is not clear to you, right? So this is probably the most important thing you can do here today. Don't move forward if you are still not certain about certain concepts. Please take that time. This is time you will never gain again in engineering if you skip this step. But with that said, please complete your takeaways and the questions that you have. And let me move on to the actual checkpoints. And let's agree that we understand how to interpret the three different support types. I showed you pictures of that help you to really take it from the real world to an idealized paper version. And we can definitely check that off now. And the next thing we talked about was reflected in the little experiment that we did virtually here, because we didn't have a classroom today, but we had a student walking over the beam. And what we understood was that the vertical support reactions really depend on the location relative to the supports of the force that was represented by the student walking on top of that beam. So that is an important concept to understand today. The closer the student came to the support, the more that support had to support. So I can check that off too. I understand that. And we then talked clearly about the three different reaction symbols, and we understand how to translate them into certain restraints or into degrees of freedom. So we need to understand that the symbols clearly identify that there is a free degree of freedom and a restricted degree of freedom. And we had a whole table about that, the one with the 3 rows that had the roller, the pin, and the fixed support in it. And I encourage you to go there if that is still a little bit questionable to you. Then we also learned that for stable structures, we need at least 3 support reactions. We will talk more about this in the future, but today we understood that we always have to give 3 support reactions. In fact, I'm going to highlight this here. I'm going to mark this as very important, because all your support reactions will only be complete if you provide 3 answers. So all your homework from now on will have 3 answers for each problem. And the same is true for a quiz and a test. And therefore, I want you to understand that here. It's very important that we agree on that. Last but not least, we learned that we can use the rotational equilibrium to really solve these support reactions. So we only talked today about simply supported beams, but in the future we will take this a little bit further. But for your homework now, you understand that you can use the moment equilibrium, rotational equilibrium, to solve for all these 3 support reactions. And therefore, we are done with the conclusion page here. I encourage you to think deeply about what you understand and what you don't understand. And I say it again because it's so important in this case. Do not move forward if there's still something muggy. Stay here and watch it again. This is a very important concept that engineers need to be familiar with before they move on to the next topic. And you will see that you will be thankful if you have a solid understanding of what we talked about today, because the rest in the future will become much easier rather than remaining a puzzle to you. But that concludes this page, and we are now ready to talk about the homework. Let's take a look at our upcoming homework and the homework that we solve for simply supported beams, particularly their support reactions. And to give you an easy way in here in problem number A, you have the same forces that are acting at the same distances, right? So here everything is B, B, B. That means that the force F2 and the force F2 here act at the third points. So think of this as 2 students with the same weight walking over the beam that stand actually at the same distance. Remember the scale example that we had here in the class today? So that is similar to what you see here. And you can just superimpose the results. So that gives you a nice, easy way to apply your own numbers and to study the knowledge that you just gained and to apply the knowledge that you just gained. And I believe you can definitely solve this problem with ease. But then let's get a little bit more intricate here, and let's actually change up the numbers. So here you see F1, F2, F3, F4. They're all applied with different values, but at equal distances. And that will also teach you one specific thing about how these forces apply. But I believe that's also easy enough, and if you paid attention in the video, that should be not too difficult. Of course, we also want to practice the knowledge that we gained through the forces under angles. So you have forces here at different angles and different distances. But just as before, all you have to do is draw the free body diagram and then calculate the support reactions. And that is everything you have to do for this problem. Now it becomes really interesting, at least in the classroom, I always get feedback on this question. And that is because it's challenging for students to grasp the angle here or how it applies to the system. So let me help you out with that. So remember that here, this symbol here has a specific meaning, and I explained that throughout the lecture, so I don't have to repeat that here right now. But there's definitely a force that is perpendicular to that surface. Sometimes there's also one that's parallel to the surface. But understand that in this case, the surface defines in which direction you have to find your support reaction. And so these 2 forces here actually act a little bit different if the support is angled. I mean, the forces act the same, but the support reaction reacts slightly different. but you can use your moment equilibrium to find the support reaction on both sides. And then please understand that you can always break this down into components that are vertical and horizontal, and together they might make the perpendicular component. But maybe I gave too much away now. But anyways, you can solve this problem. Just pay close attention to the surface and what that means to the support reaction. But if you really think about it, I think you will have no problem solving that. And then here, I understand that we did not talk about this in class today. There is something identified as M1 with a rotational sense and M2 here. So these are moments. This was not clarified in today's lecture, but this is on purpose because we want you to attempt these problems without us showing you every bit of the way. So just give it a try. This is not meant to not teach you something or to challenge you on something that we haven't taught you. We will teach you this in the future, but this is supposed to challenge you so that you can actually struggle through the problem before we will ask you and teach you how to do that properly. So that brings us to the last problem, which has a similar challenge in it. And again, don't get frustrated if it's complicated. That's not how engineers feel about solving problems, right? Engineers get excited when they have a problem that they don't know how to solve. It's what they are set out to do, figure out the challenge, and just give it a try. If you don't get it, it's not a bad thing. Before you turn in this entire homework, you will definitely get directions on how to deal with these moments. But there are two moments in this case, and we have a force that is a concentrated force somewhere in the middle of the beam, or like somewhere throughout the beam. And that are all the homework problems that you have to solve for homework 5A. And this is exclusively for simply supported beams. I wish you good luck with that, and I see you in the next lecture. Stay safe.